Hello there, and welcome to Science for Sleep, where curiosity takes a quiet breath and drifts into the kind of questions that don't usually fit between busy schedules or glowing screens. Tonight, we're going to peel back something that most of us never think about, even though it's quite literally all around us: reality. What is it really made of? Is it a single, solid thing that we move through without question? Or is it layer after layer stacked in ways we can't always see or even feel? Tonight, we're going to take a slow, careful walk through those layers, not to solve every mystery, but to rest inside them for a while. But before we start digging down through the hidden scaffolding of the universe, let me ask you something. Where are you listening from right now? Is it late where you are, or early? Maybe the kind of hour where the world outside is quiet enough that you can almost hear the hum of your own thoughts. Is there a lamp on somewhere near you, casting a small pool of light? Or are you already in the dark, letting the glow of a screen paint everything in that soft blue haze that makes time feel slower? If you found your way here because you like the sound of a calm place to think while the rest of the world doesn't ask you for anything, then I'd be grateful if you gave this a like, maybe even subscribed. It helps this little space of quiet wanderers reach other people who might be staring at their ceiling tonight and wondering, not about bills or emails, but about the strange hidden shape of everything we live in. So settle in, let your shoulders drop, and let's start somewhere simple, though simple might not stay simple for long. Because the thing about reality is that the closer you look, the less it seems to sit still. You can hold a rock in your hand, and it feels solid. It feels permanent. It feels like the kind of thing that should stay exactly as it is forever. And yet, if we could somehow shrink ourselves down far enough, we'd see that rock is almost entirely empty space, its atoms like tiny whirlpools of probability spinning in ways that seem more like music than matter. It's a strange thought, isn't it? To realize that the very ground we stand on is mostly nothing, a scaffold of invisible forces that we don't feel only because we're far too big to notice. But let's not rush there too quickly, because the top layer of reality, the one we walk around in every day, is easy to take for granted. Our world is full of solid surfaces, coffee cups, wooden tables, pavement underfoot. We trust these things without thinking, because if we didn't, we'd never move. We'd never sit down. We'd never let our guard down enough to close our eyes and rest. The world works because it pretends to be simple, and most of the time that's exactly what we need. But if you let yourself think about it for too long, cracks begin to show, not dangerous ones, but little gaps where bigger questions slip through. Questions about why anything feels solid at all, or why objects stay in place, or why you and the chair you're sitting in don't just fall through each other in some kind of quiet disaster. Those questions have answers, but the answers don't look anything like what we see at our scale. And that's where the descent begins. The first layer is the familiar one, the surface world of touch and sight and sound. And then you go a little deeper and the rules begin to bend. Not break exactly, just shift. Like looking at a reflection in water that wobbles when you move a little too close. At the next layer you find atoms, tiny and restless, held together by forces you never feel, but that never stop working, binding everything you know into the shapes you recognize. Each one made mostly of empty space, and yet somehow enough to build mountains and oceans and everything else that convinces us reality is solid and reliable. And if you go still deeper, those atoms come apart. They're pieces more like hints than things. Quarks and leptons, particles that aren't so much objects as they are blurs of possibility. They're not little marbles. They're more like probabilities pinned down only when you look too closely. And even then, not for long. And that's where something curious happens. Reality begins to look less like a place and more like an interaction. The kind of thing that only exists because it's being looked at or measured or held in some network of relationships too deep for us to see. And that's only the beginning, because further down you find rules that feel more like riddles, space that curves, time that stretches, particles that vanish into entanglement, like they're sharing a private joke faster than light could ever carry it. And if you keep going, you start to wonder whether there even is a bottom to any of it. Maybe every layer is just sitting on top of another layer, and the closer we get, the more it slips away. Like a horizon that keeps moving no matter how far you walk. But before we sink too far, let's stay here just a little while longer, at this threshold between the familiar and the strange. Because this is the place where those two worlds blur. It's the place where you can still reach out and touch the ordinary, while knowing just underneath it there's something stranger waiting to be noticed. And maybe that's why this question has stayed with us for so long. Maybe that's why so many of the world's oldest stories start with the same kind of quiet suspicion that what we see isn't all there is. You can hear it in myths about hidden worlds tucked just out of reach, in the old idea that reality might be a stage built over something deeper, or even in the way science itself keeps peeling back what it thought were the final answers only to find more. And that's what we're going to do here. Not in a hurry, not with the kind of urgency that demands conclusions, but slowly, layer by layer, as if the universe itself were inviting us to stay a little longer, look a little closer, and see how many layers it really has. So take another breath and let the surface settle, because in a moment we'll begin to slip through it, not with our hands or our eyes, but with the kind of attention that doesn't mind if the answers come slowly. We'll move past the surface and into the hidden scaffolding, where atoms hum and probability flickers, and maybe, just maybe, the layers of reality will stop feeling like something far away and start feeling like the ground you're already standing on. Now that we've settled into that quiet place where the surface of things has stopped feeling quite so certain, it's time to follow the question that has been waiting underneath all the others. The one that doesn't ask for quick answers or clever definitions, but simply lingers like a shadow in the corner of every scientific paper, every philosophical debate, every late-night moment when the world is quiet enough for you to hear your own thoughts. What exactly is reality? It sounds almost too obvious to ask, doesn't it? We live in it. We touch it. We wake up in the same room every morning with the same ceiling and the same walls, and nothing about it feels in doubt. But the moment you look a little closer, the moment you ask what it's really made of, that's when the ground beneath your feet begins to tilt just slightly. And suddenly, you're not entirely sure where the edges of the question even are. Because it's not just a matter of atoms or space or time. It's about why any of this fits together at all. And maybe that's why this question sits so deep. It's not just about science. It's not even just about philosophy. It's the kind of thing that sits quietly at the back of the mind every time you hear about quantum mechanics, or dark matter, or any of the other strange corners of the universe, and you wonder for just a second if what you're seeing day to day is only the thinnest outer layer of something much larger. You could start with physics, and a lot of people do because physics has a way of making reality feel clean and manageable. It talks about particles and forces and equations that look neat enough to pin to a chalkboard. But the deeper you go, the less solid it all becomes. An atom isn't really solid. A particle isn't really a particle. It's a smear of probability that only sharpens when you measure it. Even the space between things isn't just nothing. It's filled with fields that ripple with energy like an ocean we can't see. So is that reality, or is that just another map? And if it's a map, then what is it a map of? And then there's the way your brain quietly rewrites the world for you without asking for permission. What you see, what you hear, what you feel, these are not direct photographs of reality. They're reconstructions, stitched together by neurons that are far more interested in keeping you alive than showing you the unfiltered truth. Your mind edits colours based on context. It fills in blind spots you didn't even know you had. It even smooths over the fact that everything you experience is delayed by the time it takes your senses to process it. So in a way, the world you live in is already a version of reality built to be convenient, not necessarily accurate. But here's where it gets stranger. Because if your senses are building a model of reality, and physics is building another one through mathematics and experiments, and each of these models has limits, then what is the thing they're all pointing toward? Is there even such a thing as the true underlying layer, or is reality nothing but layers stacked endlessly, each one a useful tool for navigating whatever scale we happen to be standing on? This is where the question stops being comfortable, because the more you pull on it, the more it starts to undo itself. If the smallest scales of the universe don't look like objects but probabilities, and if our perception is more like a painting than a photograph, then maybe reality isn't a single thing at all. Maybe it's whatever emerges when enough pieces interact in just the right way. And suddenly, that simple word starts to feel impossibly large. And yet, we can't leave it alone, can we? Because even if it slips through our fingers, even if every answer spawns 10 more questions, there's something about this search that feels inevitable, like gravity pulling us downward towards something hidden. We name it with theories. We build experiments that smash particles together at nearly the speed of light. We launch telescopes into the void to catch light that's been travelling for billions of years. All because, somewhere deep down, we can't quite shake the feeling that if we can just keep peeling away the layers, we might finally see what's underneath. But there's a quiet danger in that hope too. Because what if there is no underneath? Not in the way we expect. What if reality isn't a single floor you can stand on, but a staircase that never ends? What if every layer is just another step, leading you down into smaller scales and stranger rules, until eventually you stop asking what's at the bottom and start realizing there may not be one at all? And maybe that's not such a bad thing, because there's a kind of beauty in the endlessness of it. The way the universe refuses to be wrapped up in a single neat answer. The way every discovery seems to open a door rather than close it. It means there will always be something left to wonder about. Always another quiet question waiting under the one you just asked. And perhaps that's why this question, the question beneath all questions, never quite lets go. Because even if we never reach the final layer, even if there isn't one, the act of looking changes us. It pulls our attention away from the ordinary hum of the day and points it towards something wider, something deeper. It reminds us that we're not just moving through reality, we're inside something far bigger and stranger than we usually allow ourselves to notice. So let's not rush past it. Let's stay with it for a little while longer, because if we're going to wander through the layers of reality, we might as well start with the one question that will follow us all the way down. And if you're still here, still listening, still curious enough to let the noise of the day fall away, then we're ready to take the next step downward. And this is where it gets truly strange, because the next layer waiting just beneath this one doesn't look like anything you've ever seen. It's smaller than sight, faster than thought, and yet somehow it's the foundation everything else stands on. The world of atoms, quarks, and the restless little pieces that don't sit still long enough to be what we once thought of as matter at all. And if you're ready, we'll follow them down, because reality is about to stop behaving the way we expect it to, and start showing us just how many layers there really are. If we've been circling around the question of what reality really is, this is the first place where it stops feeling familiar, where everything we think of as solid begins to melt into something smaller, stranger, and harder to hold on to. The world of atoms, quarks, and the restless foundations hiding beneath everything you've ever touched. On the surface, atoms sound simple enough. You've probably heard about them so often that the word has lost its weight. Little building blocks of matter, neat and tidy things with a nucleus in the middle and electrons circling like tiny planets. But that picture, the one most of us first learned, is just a kind of comforting sketch. A placeholder that works well enough for chalkboards and textbooks, but not for the actual universe. Because the closer you look, the less those atoms behave like little marbles, and the more they turn into something far harder to pin down. An atom is mostly empty space. If you could blow one up to the size of a cathedral, The nucleus would be a speck of dust floating somewhere in the middle, and the electrons wouldn't even be tiny planets. They'd be clouds, faint smears of probability that only sharpen into something definite when you force them to be measured. Everything between them would be nothing, vast stretches of nothing. And yet, that emptiness is what holds you up right now. It's the reason the chair beneath you feels solid, and the floor doesn't just swallow you whole. It's strange, isn't it, to think that solidity is an illusion, not because the matter isn't there, but because it's held in place by forces invisible to you. Electrostatic repulsion keeping atoms from sliding through each other. The Pauli exclusion principle, whispering that no two particles can share the same space, like some deeply ingrained cosmic etiquette. Reality, at this scale, isn't solid. It's structured, an invisible scaffolding you never see. Because if you did, you'd spend every moment wondering how it doesn't all just collapse. But if atoms were the end of the story, it would almost be simple. They'd be small, yes, but they'd at least be things we could picture. Little spheres stacking together into everything else. But atoms themselves are made of smaller pieces, and this is where the ground really begins to give way. Protons and neutrons in the nucleus aren't solid pebbles. They're collections of quarks, bound together by one of the strongest forces in existence, the aptly named strong force, carried by particles called gluons, which act less like messengers and more like an unbreakable leash, holding quarks so tightly that you could never pry them apart no matter how much energy you used. And here's where it gets even stranger. Quarks don't exist alone. You will never find one in isolation. They come in groups, trios inside protons and neutrons, or in pairs in other short-lived particles. They are the ultimate collaborators, trapped forever in their little quantum teams. And if you try to separate them, the force binding them together only grows stronger, until the energy you pour in creates new particles entirely. It's as if reality has built a rule that says, if you dig too deep, you won't find a single thing. You'll just find more of the same. And then there are electrons, skimming around that empty cathedral of the atom. Not orbiting like planets, but existing as probability waves spread out in regions called orbitals. You can't point to where an electron is. You can only say where it might be, and if you dare to look, you change it by the very act of observation. It's as though the universe has drawn a line here, a quiet reminder that you don't get to watch without leaving fingerprints. All of this leads to a strange realization. The foundation of everything is not built out of little bricks. It's built out of rules, patterns, interactions, things that refuse to sit still or even exist in the way we usually mean the word. Everything you touch is made of particles that are barely ever in one place. Particles that only behave like things because countless underlying relationships hold them in place. And yet, somehow, out of all this restlessness emerges the ordinary world. The one where you can set down a cup of tea and trust it won't fall through the table. The one where you can walk across the floor without even thinking about the unthinkable machinery running underneath you. But the hidden foundations don't stop there. Because once you begin to see that reality is made not of objects but of interactions, another question comes rushing in. If the smallest things are not truly solid, then what exactly are they made of? And this is where physics dips into something even stranger. Fields. Because underneath quarks, underneath electrons, underneath every particle that has ever existed, there are fields. Invisible oceans that fill all of space. Even the places you'd think of as empty are humming with them. Every particle you've ever heard of is not a self-contained little bead. It's an excitation, a ripple in one of these fields, like a note played on a cosmic instrument. Quarks are just disturbances in the quark field. Electrons are ripples in the electron field. The universe is not made of particles, not really. It's made of the fields that give rise to them, and that means what we call matter is simply what happens when these fields stop being quiet. And if you sit with that for a moment, the ordinary world starts to feel very different, because it means the difference between nothing and something isn't a sharp divide. It's a matter of how loudly the underlying fields are singing. Every atom, every quark, every piece of you, and every piece of the chair you're sitting in is just the universe vibrating in particular ways. But before that idea drifts too far into the abstract, remember this: it's not just theory. We've seen this hidden structure in experiments, smashing particles together at nearly the speed of light, watching quarks spray out like fireworks, reading the traces they leave in detectors so sensitive they can count events that happen in less than a billionth of a second. We know the foundations are there because when we push hard enough, reality shows us its wiring, even if only for an instant. And yet, for all the certainty we've scraped out of these glimpses, there's a kind of strangeness that refuses to go away. Because if matter is nothing more than organised emptiness, and particles are just ripples in deeper fields, then what exactly is the thing we call real? And if there's another layer waiting beneath these fields, something even more fundamental hiding under every quark, every electron, every empty gap between them, would we even know how to see it? Those are the questions that wait for us next. But for now, we can sit here at this first hidden layer and take in just how far we've already come from the ordinary surface world. Because the deeper we go, the less reality looks like the solid floor we once thought it was, and the more it begins to look like an intricate machine running quietly under our feet. A machine that somehow holds everything together, even when most of it is nothing at all. If atoms and quarks already seem strange, what waits beneath them is something that doesn't just stretch our understanding. It quietly pulls it apart. This is the quantum stage, a place where certainty dissolves, where the neat boundaries we use to hold the world together blur, until all that's left are probabilities, shifting patterns, and rules that refuse to behave like rules at all. The first thing to understand about this layer is that it doesn't care what we expect. At our scale, the world is predictable. If you drop a ball, it falls. If you turn on a light, the room brightens. Cause leads to effect, and the sequence is steady enough that you can live your whole life without ever questioning it. But at the quantum level, that familiar rhythm breaks down. Here, particles don't move from one place to another in a clean line. They exist in a haze of maybes, each possibility waiting until the moment you look, as if reality itself has been holding its breath. Imagine an electron. In the world we know, it should be here or there, but down here, it is neither. It is spread out like a mist, a wave of probability filling every space it might possibly be. Only when you measure it, only when you force the question does it choose. And even then, it doesn't move in the way we would expect. It simply appears in one location as if the act of observation collapsed every other option out of existence. This isn't a metaphor. This is how the universe operates at its smallest scales. It gets stranger. If you place two particles far apart, miles apart, light years even, and link them through a property called entanglement, something unthinkable happens. Change one particle, and the other changes instantly, as if distance doesn't matter at all. It's not a signal moving between them. Nothing travels. It simply happens, everywhere, all at once. Einstein himself called it spooky action at a distance, because even he, who reshaped our idea of time and space, couldn't quite accept it. But experiment after experiment has confirmed it. Reality at this level isn't local. It isn't limited by space the way we think it should be. And then there is the uncertainty principle, that quiet rule at the heart of all this. It says you can never know both where something is and how fast it's moving with perfect accuracy. The more you know about one, the less you know about the other. It isn't a flaw in our tools or a gap in our understanding. It's how the universe works. Certainty itself is forbidden, and yet in this sea of uncertainty, the universe still manages to build everything. You, me, the stars, every rock and river and quiet late-night moment. This is the paradox of the quantum stage. Beneath the solid and the certain is a world that has none of those qualities, and yet it somehow gives rise to all of them. Even stranger is the fact that these quantum rules don't just exist in theory, we've learned to harness them. Quantum mechanics gave us lasers, transistors, the very foundation of the device you're using right now. It's proof that even in a world where nothing is certain, you can still build something reliable. It's as if the universe is whispering, yes, the rules are strange, but they are still rules. But for every answer, there's another question. If particles can exist in many places at once, if they can influence each other across impossible distances, and if even observation itself can change what happens, then what exactly are we looking at? Is reality something that exists on its own, or is it something that only comes into focus when it's noticed? This is the layer where scientists argue late into the night because the math works perfectly, but the meaning refuses to sit still. Some say particles are waves of probability until we measure them. Others say the universe splits, branching into countless versions every time a particle chooses. And still others wonder if the question itself might be wrong, if maybe what we call reality is just one way of describing something deeper, something we haven't yet learned to see. And the most unsettling part, every test we run only deepens the mystery. Quantum mechanics doesn't break. It never fails. It simply refuses to tell us what it all means. And maybe that's why this layer is so hard to look away from. Because once you glimpse it, once you understand that beneath the familiar surface there is a world where certainty isn't real, you can't help but wonder what other layers might be hiding even further down. But before we move to those, let's sit here for a moment in the strangeness of it. Because this is the point where the ordinary world ends, and it's only when we stop expecting it to behave like home that we can take the next step. If this quantum stage shows us that reality isn't solid, the next layer will show us that it isn't even local. It's where distance, separation, and space itself stop being what we think they are. It's the place where particles act like they share a single mind no matter how far apart they are. If the quantum stage already felt like it had stripped away the comfort of certainty, what waits here is something that goes even further. This is where space itself starts to feel less like a barrier and more like an illusion. This is the realm of entanglement, where distance doesn't matter, and the universe quietly ignores the rules we thought it was following. Entanglement is one of those ideas that sounds impossible until you realize it isn't just an idea at all. It's a fact. If you take two particles and link them in a very particular way, they stop behaving as separate things. From that moment on, no matter how far apart you move them, they act as if they are still connected. Change one, and the other changes instantly. There is no signal racing between them, no delay, no hint that space or time even came into the conversation. It just happens, everywhere at once, as if the universe itself refuses to acknowledge the gap between here and there. Einstein hated this. He called it spooky action at a distance, partly because it seemed to violate everything he believed about how the universe should work. Nothing, he argued, could move faster than light. Information couldn't leap across space in an instant. And yet, here was a phenomenon that seemed to do exactly that. And worse, it did it in a way that didn't even look like movement. It was as if the two particles had never truly been apart to begin with. Today, we've tested this in every way imaginable. We've entangled photons and sent them miles apart, fired them through fiber optic cables, bounced them off satellites orbiting above the Earth. No matter what we do, no matter how far we stretch the distance, the connection remains perfect and immediate. There's no fading with distance, no gradual weakening of the effect. It's as if distance isn't even real at this level, only a kind of surface detail that matters to us but not to the deeper machinery running the universe. And that's what makes entanglement so unsettling. Because if two particles can act like one thing no matter how far apart they are, then the line between here and there starts to blur. Maybe reality at its deepest layer doesn't see space the way we do. Maybe there's no gap to cross because fundamentally, everything is already part of one connected whole. And yet, as strange as this is, it's not just a curiosity for physicists to argue about in quiet conference rooms. We've started to use it. Quantum computers, for instance, rely on entanglement to process information in ways no classical machine ever could. Quantum cryptography uses it to create code so secure that not even the laws of physics would let anyone break them. This isn't just a philosophical puzzle, it's technology. It's proof that the rules of this strange layer of reality are not only real but practical, if you're willing to accept how alien they are. But here's the part that almost no one talks about outside of physics circles. Entanglement doesn't have a limit. You can entangle 2 particles, but you can also entangle 3, or 10, or billions in theory. The mathematics doesn't stop. Which leads to a quiet, unsettling question. If entanglement is this natural, this fundamental, how much of the universe is already connected in ways we don't see? It's not a comforting thought, but it's also not a frightening one. It's something deeper than either. Because if entanglement is everywhere, then every boundary we think is solid. Between here and there, you and me, even one star and another, might only be true from the narrow view we live in. From the layer beneath, it might all be one thing. And that idea has consequences. It forces us to wonder whether what we call separation is just a convenient illusion for creatures who have to live at our scale. Maybe the universe is less like a vast empty space scattered with pieces and more like a single web, one in which every strand quietly hums with the motion of every other strand. And if that's true, then what does it mean to look deeper? Because entanglement isn't the end of the story. It's a doorway. And what waits beyond it is stranger still. Because once you see that distance doesn't matter, the next question is whether the very things that look solid and separate at all, the objects, the walls, the ground under your feet, are as real as you think they are. Once you've seen that particles can be linked no matter how far apart they are, you can't help but wonder what else might not be what it seems. Now that we've seen particles blur into waves and watched entanglement erase the meaning of distance, it's time to face a truth that might be even harder to sit with. The world you see, the world you touch, the one that feels so steady and reassuringly solid, it isn't. Solidity is an illusion, one so convincing that we build our entire lives on it without ever noticing that it's not really there. Start with the simplest example, the chair beneath you. It feels solid because you don't fall through it. Your body presses down, the chair presses back, and in that quiet agreement is all the certainty you need. But if you could shrink yourself down far enough, if you could pass through skin and bone and atoms and all the empty space between them, you'd find almost nothing there. The particles that make you and the particles that make the chair never actually touch. They repel each other, held apart by electromagnetic forces. The sensation of sitting, of pressure, of contact, that's not atoms meeting atoms. It's the force fields between them refusing to overlap. In reality, you're hovering ever so slightly above everything you believe you're touching. This is the first crack in the illusion. The solidity you feel is a trick of forces, not matter. And that matter, when you look closer, is already mostly emptiness. Take a single atom. If its nucleus were the size of a marble, its electrons would be orbiting at a distance of several football fields away. Everything in between, empty. And yet, stack enough of these ghostly structures together and you get wood, stone, steel, things that feel unyielding enough to stop a fall or build a bridge. The deeper you go, the stranger it gets. Even the particles that form those atoms are not little billiard balls. They're not solid. They're excitations in fields, vibrations in an invisible sea that stretches across the universe. What we call matter is really patterns in those fields, stable arrangements of energy that give the illusion of something firm. In other words, what you see, what you feel, and what you think of as solid ground is just organised motion in an otherwise restless void. And yet, this illusion is so complete that it's almost impossible to break. Your brain was built to accept it. Every sense you have is designed not to reveal what reality truly is, but to give you a simplified version you can live in. If you could somehow feel the gaps between the atoms in the floor, or sense the electromagnetic forces holding you above it, you'd never be able to move without thinking about the strangeness of it all. So instead, evolution hands you a simplified world, a version that feels stable enough to survive in, even if it hides the fact that nothing underneath it ever stops moving. And maybe that's the real marvel here. The world is built from forces and emptiness, from particles that never settle down, and from rules that care nothing for human intuition. And yet, out of that chaos comes the ordinary, a table you can lean on, a door that opens and closes, a planet that carries you through space without falling apart. But knowing the illusion is, there does something to you. It changes the way you see the world. When you pick up a stone, you can imagine the atoms inside it humming like a quiet orchestra. When you touch a wall, you can remember that what you're really feeling isn't contact at all, but a field of invisible forces pushing back against you. Solidity stops being obvious and starts feeling almost miraculous, something that only happens because an entire hidden layer of physics never stops working beneath it. And if you follow this far enough, you begin to wonder, if solidity is an illusion, what else is? If what feels most certain is really a product of unseen rules, then how many of the other things we take for granted are built on the same kind of hidden scaffolding? Because if there's one thing this layer of reality teaches, it's that the world doesn't have to be what it seems to be in order to hold together. And that thought leads us down to the next layer, where the invisible becomes even more important. Because underneath all the emptiness, beneath the particles and their forces, there's something even stranger shaping everything we see. Not matter, not motion, but a hidden sea of energy that fills every corner of space, even in places where there is supposedly nothing at all. If solidity was only an illusion, and emptiness turned out to be the stage on which everything happens, then the next layer takes us somewhere even stranger. It's the part of reality we never see, but that is always there, shaping every atom, every particle, every breath you take. This is the invisible sea, the vast network of energy fields that fill the universe, even in the places we used to call empty. For a long time, people thought of space as nothing, a true void, a backdrop for stars and planets to float in. But the closer we looked, the more it became clear that space is not empty at all. It's alive with structure. It's threaded with fields, quantum fields, stretching in every direction, everywhere, all the time. They don't stop at the edge of galaxies or fade into some unreachable distance. They're here, right now, passing through you, through the floor beneath you, through the air in the room around you. Every particle you've ever heard of is just a ripple in one of these fields. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Quarks, the pieces of protons and neutrons, are ripples too, bound into their own field. It's as if the universe is a kind of invisible ocean, and everything that exists, every star, every planet, every bit of matter you can see, is just a set of waves rising and falling on its surface. And here's the strangest part. Even in places where you'd swear there's nothing, no particles, no heat, no light, those fields are still there. They never go away. They hum quietly at what physicists call the vacuum state, which sounds like it ought to be nothing at all, but it isn't. The vacuum is restless. It seethes with tiny fluctuations, particles popping in and out of existence so quickly that you'll never catch them, but their effects are measurable. Even nothing has weight in this universe. You might think that sounds impossible, but we've seen the fingerprints of this invisible sea. The Casimir effect, for example, where two uncharged metal plates placed close together are mysteriously pushed toward each other. Why? Because the quantum fields in the space between them shift and create a tiny imbalance, as if the vacuum itself decided to give them a gentle nudge. It's proof that even the quietest parts of reality are never truly still. And then there's the Higgs field. For decades, it was only an idea, a whisper in the equations that hinted that without it, nothing would have mass at all. Matter would still exist, but it wouldn't have weight, wouldn't form stars or planets or people. And then, in 2012, we finally saw it. The Higgs boson, a particle born from this field, proof that the invisible scaffolding we'd only guessed at was real. The field had been there all along, holding the universe together while we lived our entire lives never feeling it, never seeing it, but depending on it completely. It's unsettling in a way to realize that the world we move through is propped up by layers of reality we never directly touch. The air around you, the space between galaxies, even the quiet stretch between particles inside an atom, they're all soaked in this invisible sea of fields, humming silently while the visible world dances on its surface. But this is what makes it so extraordinary, because if there's anything that can change the way you see reality, it's this. You're not just walking through empty space. You're swimming in a vast ocean of hidden energy. Every step, every moment is surrounded by it. And if this is what lies beneath the world we know, then what's deeper still? If fields fill the universe, shaping every particle, what are they woven into? What's the foundation beneath the invisible sea itself? We've reached a layer that doesn't just sit beneath everything else, it is everything else. This is where space and time stop being two separate ideas and merge into one continuous fabric, a stage so fundamental that everything we've talked about so far, from atoms to fields, exists only because it's stretched out across it. This is space-time, and it's not the unshakable backdrop we once imagined. It's alive, it bends, it warps, and it quietly dictates the shape of the universe. For centuries, we thought of space as nothing more than emptiness, a vast container for the stars and planets, and of time as a steady river flowing at the same rate for everyone, everywhere. Isaac Newton himself imagined them that way. Two separate absolutes, the unchanging foundation on which the drama of the cosmos played out. But then came Einstein, and with him a revelation that would turn everything inside out. Space and time, he showed, are not separate things. They are one, and this one thing is flexible. The simplest proof of this is gravity. For most of history, we thought gravity was a force, an invisible hand pulling objects toward one another. But Einstein saw it differently. He realized that what we call gravity isn't really a force at all. It's the shape of space-time itself. Imagine a massive object like the sun. It doesn't pull planets toward it the way a magnet pulls metal. Instead, it bends the fabric of space-time around it, and the planets simply follow the curves. They're not being dragged. They're falling freely through a landscape shaped by mass. And we've seen this bending of space-time with our own eyes. Light from distant stars bends as it passes near massive objects, as if space itself has been tilted. GPS satellites orbiting above our planet have to correct their clocks for the warping of time caused by Earth's gravity. Black holes, those bottomless wells of space-time, don't just bend it. They twist it into something so steep that nothing, not even light, can escape. These aren't just theories. We've measured them. We've photographed them. Space-time is real. But here's the part that's hardest to wrap your head around. Space-time isn't just a stage that matter moves across. Matter and energy can change space-time, and space-time in turn tells matter how to move. The two are locked together in a kind of endless conversation. Every step you take, every object in the room around you, even the warmth radiating from your own body, all of it presses on space-time, reshaping it ever so slightly. It's not enough for you to notice. but it's there, woven into the structure of the universe like an invisible thread. And then there are the ripples. For a long time, they were only an idea, a consequence of Einstein's equations, gravitational waves, tiny distortions in space-time that ripple outward whenever something massive moves violently enough. Two black holes colliding, neutron stars smashing together. In 2015, we heard them for the first time. Detectors built with near impossible precision recorded space-time itself ringing like a distant bell from an event that happened more than 1 billion years ago. In that moment, the universe stopped being silent. All of this leads to a strange, quiet realization. The ground beneath your feet is not really solid ground at all. It's a curve in space-time shaped by the mass of the Earth, holding you in place because that's simply the path you follow in this warped geometry. If the Earth weren't here, you wouldn't fall upward. There would just be no curve to follow, and this is only the beginning. Because if space-time can bend, then what happens if it bends enough? What happens if the fabric of reality isn't just curved but stretched, twisted, or even torn? That's not science fiction. It's the kind of question physicists ask in serious papers. Space-time, for all its elegance, is not unbreakable. In the heart of a black hole, it's pushed to a point where its equations simply stop making sense. At the edges of the universe, it stretches faster than light itself, dragging galaxies apart with it. And maybe that's the most humbling part of this layer. Space-time isn't just where we live. It's what we live in. It's the stage, the thread, and the quiet architect of the universe all at once. And even though it feels steady, it's constantly shifting, changing shape around massive objects, rippling from cosmic collisions, expanding in ways we still don't fully understand. But the deeper you go into this fabric, the stranger it gets. Because space-time isn't the final layer either. There's something even quieter at work, something that doesn't bend or ripple but pulls, a force that shapes galaxies, holds stars in their orbits, and keeps us bound to the Earth. It's not separate from space-time, it's written into it. If space-time is the stage beneath our feet, then gravity is the quiet hand that shapes the play without ever raising its voice. It doesn't roar, it doesn't demand attention. It's the most familiar force in the universe, and yet the most elusive, a pull so constant and steady that we hardly even notice it's there, until we try to imagine what life would be without it. Gravity feels simple. It's why an apple falls from a tree. It's why the moon circles the Earth, why the Earth circles the sun, and why the sun drags its entire family of planets through the galaxy like lanterns tied to its wake. But that simplicity is deceptive. Gravity isn't just a force pulling things together. It's space-time itself, bent and curved until objects simply follow the paths laid down for them. You've been following those paths your entire life. Every step you've ever taken, every time you've stumbled or dropped something, every breath you've drawn has been under the quiet influence of this cosmic architect. It doesn't shout for your attention the way electricity crackles or magnetism tugs at metal. It hums in the background like the faintest vibration, always there, shaping every moment without asking for acknowledgement. But what's strange is how weak gravity really is. Compared to the other forces of nature, it's almost absurdly delicate. Hold a paperclip in your hand and a small magnet can pull it up against the entire mass of the Earth. Think about that for a second. One little magnet can beat the gravity of a planet. And yet, for all its weakness, gravity wins in the long run because it never turns off. It reaches across infinite distances. It binds galaxies together. It gathers dust into stars and stars into galaxies and galaxies into vast clusters that sprawl across the universe like glowing cities in the dark. And at its most extreme, gravity becomes something even stranger. Take a star many times larger than our sun, let it burn through its fuel and watch it collapse. As its mass crushes inward, gravity deepens until it becomes a trap even light can't escape. This is how black holes are born. places where space-time is pulled so tight it folds in on itself, where gravity stops being a gentle curve and becomes an endless plunge. And even though we can't see what happens inside, we can see their fingerprints. Stars whipping around invisible points in space, light bent and stretched into eerie arcs, and entire regions of space-time turned into gravitational wells so deep they reshape the universe around them. But gravity isn't only about the grand, dramatic extremes. It's in the small, quiet things too. It's in the way you feel heavier when you climb a hill because you're fighting against that curve in space-time. It's in the way time itself slows down ever so slightly the closer you are to a massive object. Yes, gravity even touches time. 2 clocks set at different altitudes don't tick at exactly the same rate. The one closer to Earth's centre, sitting deeper in its gravitational well, runs slower. It's a difference so small you'd never notice it, but satellites in orbit rely on this correction every second to make GPS work. And then there's the way gravity shapes the universe, not just in space, but in history. Without it, there would be no stars, no planets, no galaxies, no you. Every atom in your body was forged in a star held together by gravity. Every drop of water, every stone, every living thing is part of a chain of events that began because matter gathered and collapsed, pulled along by that same subtle whisper. And yet, for all our understanding of how it behaves, gravity is still a mystery. We don't know why it's so much weaker than the other forces. We don't know if it has a quantum form the way the other forces do. We've searched for a particle called the graviton, the hypothetical quantum carrier of gravity, but so far it has remained hidden. Gravity is everywhere, and yet its deepest nature is still beyond our reach. And maybe that's what makes it feel so different from everything else we've explored so far. Gravity isn't loud, it isn't sharp or sudden, it's patient, it waits, it shapes, it builds, and it does it so gently that you almost never notice that you're living every second of your life in its quiet embrace. But what happens if you follow that whisper far enough? If you trace gravity all the way down to its limits, where time slows to a crawl and space folds in on itself? That's where the edges of reality begin to fray, and the familiar rules start to give way to something far stranger. And that's where we're headed next. Because once you've heard the whisper of gravity, you can't help but follow it into the places where it stops sounding like a whisper at all, into the places where it roars. If gravity showed us how the universe bends and folds itself into shape, this next layer stretches it in an entirely different direction. This is the place where reality stops being singular, where the idea of one single, solid world starts to fracture into something stranger. This is the layer of parallel realities and branching paths, and once you see it, you can't quite look at the world the same way again. It starts with quantum mechanics, because of course it does. At that smallest, quietest scale of existence, particles don't pick a single state until they're measured. They hover in a haze of possibilities, as if every outcome is waiting to be chosen. In most interpretations, those possibilities collapse into a single result when we look. But there's another way to see it, one that refuses to throw away any of those other outcomes, one that says every single possibility happens, just not here. This is the many worlds interpretation, and it's as unsettling as it is elegant. In this view, every time a particle chooses, the universe splits. One version where it went left, another where it went right, one where it decayed, one where it didn't. Nothing is discarded. Everything that can happen does happen, just in another branch. And if that's true for particles, why not for everything else? Why not for you? Every decision you've ever made, every time you turned left instead of right, spoke instead of staying quiet, said yes instead of no, each one might exist in its own branching thread. You in this moment, listening here, in this world, and another you, somewhere else who didn't click, or didn't stay, or never found this place at all. It sounds impossible, and maybe it is, but the math of quantum mechanics doesn't rule it out. And strangely, it even solves one of its deepest puzzles, how the world we see can emerge from something so probabilistic. If every possibility happens, then there's no collapse, there's no single outcome, there's just the version of the universe we happen to be standing in. But if you follow that idea for long enough, it starts to feel heavy, because it doesn't just suggest countless other universes, it suggests that every one of them is as real as this one. You can't see them, you can't touch them. But if this interpretation is right, they're there, stitched into a larger structure we don't yet have the language to describe. And then there's the question no one can quite answer. If these other realities exist, are they truly separate? Or could they, under the right conditions, brush against each other? There are theories, mathematical whispers in the equations of quantum physics, that suggest interference between branches might be possible, however faint. Tiny overlaps, like two ghostly reflections crossing without ever quite merging. But there's another way to look at it. Maybe these parallel realities aren't out there at all. Maybe they're folded right into this one, part of the same deeper fabric. After all, if reality has layers, why wouldn't they overlap? Why wouldn't they run side by side like threads in a single weave, each one too small for us to see from where we're standing? And if that's true, then the world we know isn't the only world. It's just one path among countless others. Every event, every possibility, branching and splitting, not like roads on a map, but like roots in the dark, spreading endlessly, far beyond what we could ever follow. But here's the part that keeps this from feeling hopelessly distant. Even if those other branches are forever beyond our reach, the one you're on is still yours. And maybe that's the point. Maybe in a universe that refuses to pick a single story, meaning comes from the thread you happen to be travelling down. But the idea of branching realities leaves us with one more question. If this is how the universe works at its deepest level, then what about the world we see? What about the version of reality that feels stable enough to sit inside and trust? If there really are countless paths, why does this one feel so singular, so concrete, so unshakably real? The next layer begins to answer that. Because to understand why this world feels the way it does, we need to ask whether it's even what it appears to be, and that leads us straight into one of the most unsettling possibilities of all, that reality itself might not be what it claims to be. One of the most unsettling and strangely compelling layers of all, because if the idea of parallel realities was enough to make the ground under your feet feel a little less certain, this next one asks whether the ground is even real in the first place. This is the layer of the simulation hypothesis, the question of whether the universe is built not from particles and fields, but from something more like pixels and code. It sounds like science fiction, and for most of history it was. The thought that everything you see, everything you hear, everything you feel could be part of some vast hidden computation wasn't even a serious topic. But then our technology began to change. We built computers that could simulate weather, ecosystems, entire virtual worlds. We created video games where landscapes stretch for miles, where water ripples and light bends in ways that look uncannily real. And slowly, the line between the virtual and the physical began to blur. Not because the virtual was catching up to us, but because we started to wonder whether our world had always been running on its own hidden code. This idea took on a new weight when philosophers and physicists began treating it not as fiction, but as a genuine possibility. If a civilization could advance far enough far beyond us, it might have the power to simulate universes indistinguishable from reality. And if that's possible, then the next step is hard to avoid. What's to say we're not already inside one? At first glance it feels absurd. Surely we'd notice, wouldn't we? Surely there'd be glitches, seams, some sign that the world around us isn't quite as solid as it pretends to be. But then you start to look at the universe in a different way, and you realise that we already have glitches, just not the kind you expect. The world has a resolution limit. We call it the Planck length, the smallest measurable unit of space, below which the concept of distance itself stops making sense. It has a frame rate too, the speed of light, the ultimate speed limit, as if the cosmos updates reality no faster than that. Even the way quantum mechanics behaves begins to feel computational. Particles don't exist in defined states until they're measured, almost like a rendering engine only drawing the part of the screen you're looking at. Is it proof? No. But it's enough to make you pause, enough to make you wonder if maybe the universe is not continuous but discrete, built from bits of information, ticking forward one imperceptible step at a time. And here's the strange part. If it were true, we might never know. A perfect simulation doesn't leave fingerprints. It doesn't announce itself. You wouldn't find a hidden line of code etched into a rock or discover a menu option in the sky. You'd simply live your life inside it, unaware, because that's what the system was built to do. But not everyone agrees. Some physicists have actually proposed experiments that might, in theory, catch the edges of the grid. They look for patterns in the noise of the universe, tiny hints that reality is pixelated at its deepest level. So far, nothing has been found. But the fact that we're even asking the question says something remarkable. It means our understanding of reality has grown so strange, so abstract, that we now take seriously the possibility that existence itself is running on a kind of cosmic processor. But here's the thing. Whether or not this is true, the effect it has on how we see the world is the same. Because if the universe is a simulation, then everything in it, the galaxies, the stars, every fleeting second of your life, is still part of its design. And if it isn't, if this is all raw, unprocessed reality, then we're standing inside something just as mysterious, only without the safety net of someone or something having built it. And maybe that's the real point of this layer. It isn't about proving we're in a simulation. It's about the way the question strips reality down until all that's left is wonder. Because whether it's pixels or particles, whether the world is programmed or not, the fact remains that it runs with such precision, such elegance, that you can fall asleep under it without worrying it will glitch apart before morning. But if we are going to ask whether the universe is coded, we also have to ask another question, one that digs even deeper. Who or what is doing the observing? Because there's one more layer waiting underneath this, and it's one that turns the lens back on us. If the simulation hypothesis raised the unsettling idea that the universe might be running on hidden code, this next layer asks something even stranger. What if the thing that makes reality real isn't out there in the fabric of the universe at all? What if it's in here, behind your eyes, in the quiet, constant hum of awareness we call consciousness? Consciousness is the puzzle we can't stop circling. It feels so ordinary that we forget how mysterious it really is. You wake up, you open your eyes, and there it is. The sense of being here. Not just existing as matter, not just a collection of atoms or firing neurons, but you. The part of reality that looks out at the rest of it and says, this is happening to me. And for all the progress we've made in science, no one can explain why that happens. We can map the brain in staggering detail. We can measure electrical activity in neurons, follow patterns of thought, even watch decisions forming fractions of a second before you're aware of them. But none of that explains why any of it feels like anything. Why there is something it's like to be you, sitting here, listening to these words. And here's where this ties back to reality itself. Because if consciousness is the lens through which we experience the world, then the world you live in isn't just out there. It's also in here, reconstructed and reinterpreted by your mind. You don't see raw reality. You see a version of it filtered through attention, memory, and perception. The colours you see aren't really out there in the world. They're created by your brain. The sounds you hear aren't pure vibrations. They're transformed into something your mind can understand. And if that's true, then how much of reality is really independent of the observer? Quantum physics has already shown us that, at the smallest scales, observation changes what happens. An electron isn't anywhere specific until you look. A wave of probability collapses into a single point the moment you measure it. For years, physicists argued about what this meant. Is the universe fundamentally unfinished until something conscious looks at it? Or is it simply that our measurements fold us into the story, whether we want to be there or not? Some theories go even further. They suggest that consciousness might not just be a passenger in reality, it could be one of its foundations. Thinkers like John Wheeler, one of the great physicists of the 20th century, proposed the idea of a participatory universe, where observers aren't just watching reality unfold but helping to bring it into being. Not because we will it to happen, but because the act of noticing might be woven into the way the universe itself works. But even if that's not true, even if consciousness is just what happens when brains become complicated enough, the fact remains, everything you know about reality is tied to it. Without consciousness, there's no colour, no sound, no sense of time passing. The universe could be full of stars and galaxies, but without awareness to witness it, there's no story. It would just be events unfolding in silence, and that's what makes this layer so different from the others we've passed through. The deeper we've gone, the less human the universe has seemed. Atoms don't care about you. Quantum mechanics doesn't wait for permission. Spacetime bends whether or not you're watching. But here, in this quiet question of consciousness, the universe suddenly feels personal. Not because it's made for us, but because without this strange spark of awareness, none of it would mean anything at all. And maybe that's why no one can quite pin consciousness down. Every time we think we're close, it slips out of our hands. Maybe it isn't something you can measure in a lab or reduce to equations. Maybe it's a layer of reality that doesn't sit underneath everything else, but instead runs through it, connecting the rest of the layers in a way we don't yet understand. But if consciousness is the lens, and reality is what we see through it, then what happens if the lens itself is limited? If there are things out there, things all around us that we simply can't perceive because we weren't built to notice them? If there's one thing every layer of reality has taught us so far, it's that there's always more hiding just beyond what we can see. And sometimes the only way to find it is not by looking deeper, but by changing how we look. If consciousness is the lens through which reality comes into focus, then this next layer is what gives that reality its hidden structure. Underneath particles and fields, beneath space-time and even the strange role of the observer, there's something colder, cleaner, and strangely elegant. Mathematics. It's easy to think of math as nothing more than a tool, something humans invented to count, to measure, to keep track of things. But the deeper we look into the universe, the more it seems that math isn't just a language we use to describe reality. It might actually be the language reality is written in. You can see it in the way the laws of physics are expressed, not in words or images, but in equations. Einstein's field equations for gravity, Maxwell's equations for electromagnetism, Schrödinger's equation for quantum mechanics, all of them reduce the infinite complexity of the universe into symbols on a page, and those symbols work. They predict planets moving in their orbits with perfect precision. They describe the way particles behave at scales so small that no eye will ever see them. But here's what's truly strange. Mathematics doesn't just describe what we already know. It goes further. It predicts things we haven't seen yet. Neptune was discovered because of math. So was the Higgs boson. Even black holes, those monstrous wells of space-time, were once nothing more than mathematical consequences, scribbled into existence on paper, long before we found any proof they were real. And that raises a quiet, unsettling question. Why does math work so well? If it were simply a human invention, a tool for bookkeeping, why should it map so perfectly onto the fabric of the universe? Why should the same equations that govern the arc of a thrown stone also explain the path of a galaxy? Some thinkers have taken this further than most would dare. Physicist Max Tegmark has argued that maybe the universe isn't just described by mathematics. Maybe it is mathematics. In his view, every physical thing is ultimately a mathematical structure, an arrangement of relationships and rules that exist independently of whether anyone is there to write them down. In this picture, matter, energy, and even space-time itself are just shadows cast by a deeper, purely mathematical reality. And strangely, the more we uncover, the more this idea feels plausible. Particles follow symmetrical patterns as if they were notes on a scale. Quantum fields obey mathematical rules so precise that even the slightest deviation would tear the universe apart. Nature doesn't just allow math, it seems to run on it, like code running on a cosmic machine. But here's where this becomes truly humbling. If mathematics is the foundation, then the universe is built from something that doesn't care whether it's seen or understood. Numbers don't need us. Equations don't vanish when no one's looking. If the universe is mathematical, it means it was always there, its structure waiting to be discovered like an unplayed melody in an instrument far older than we are. And yet, for all its starkness, there's something strangely comforting about this layer. Because in the cold, quiet logic of mathematics, we find a kind of certainty that the rest of reality doesn't give us. Particles flicker in and out of existence. Time bends and stretches. Even observation seems to change the outcome. But the math beneath it doesn't waver. It's the bedrock. Still, this layer leaves us with a deeper question. If math is the language of reality, who or what is doing the reading? Is the universe simply playing out its equations blindly, or is there something in the way those equations give rise to structure, complexity, and life that points towards something even deeper, something that goes beyond the symbols themselves? If mathematics gives reality its hidden structure, this next layer is where structure turns into something more. This is the place where rules give rise to patterns, and patterns give rise to worlds. This is emergence, where complexity blooms out of simplicity and builds the reality we live in without anyone ever needing to design it. Emergence starts small. Imagine a single water molecule. By itself, it doesn't flow, it doesn't ripple or crash or freeze into ice. It just exists quietly. But gather enough of them, and suddenly you have waves, rivers, storms. Properties appear that weren't there in any single molecule. You can't point to one drop of water and say, this is where wetness lives. Wetness only exists when the pieces come together. The same is true everywhere you look. An ant on its own is just an insect, following simple rules. But put it in a colony, and those rules create something larger. Complex networks of tunnels, coordinated foraging, entire societies built from instincts too small to explain the result. No one understands the whole. It doesn't have to. The colony emerges from their collective behaviour. And this isn't just a quirk of biology. The very universe itself works this way. Atoms, following the basic laws of physics, gather into stars. Stars gather into galaxies. Galaxies gather into vast filaments that stretch across the cosmos like a web. At every scale, the pieces obey simple rules, but when enough of them come together, those rules build something new, something greater than the sum of the parts. And that's what makes this layer so powerful. It tells us that reality isn't just stacked downward toward the smallest things, it's also stacked upward, from quarks to atoms, from atoms to molecules, from molecules to life, and then, astonishingly, from life to minds that can sit here and think about the layers beneath them. But emergence doesn't just explain how complexity happens, it also reshapes the way we see reality itself. Because if the universe is emergent, then the things we take for granted, solid objects, living systems, even consciousness, aren't fundamental. They're the products of countless smaller interactions weaving themselves into something larger. The world is not built from objects sitting side by side. It's built from processes, each one layering itself over the last until you can't see the individual steps anymore. And here's what's even stranger. Emergence is not planned. There is no blueprint, no architect sketching the design. It simply happens because the rules allow it to. Life didn't appear because someone wrote it down. It appeared because chemistry, under the right conditions, began stacking itself upward until something unexpected came out of the mix. And yet, despite its simplicity, emergence is how the universe hides its greatest magic. Because if you look at any one layer, particles, atoms, molecules, you won't see a hint of what comes next. Nothing about a lone neuron explains what it's like to have a thought. Nothing about a single snowflake predicts the shape of an avalanche. The higher layers are invisible from below, but they're just as real. And this is where the layers of reality stop feeling like separate floors in a building and start feeling like a single, endless climb. Every level builds on what came before, and somewhere far above us are structures we can't even imagine yet, because we're still standing too low to see them. But here's the part that's most unsettling of all. If reality emerges upward, then maybe there's no top. Maybe complexity keeps stacking forever. Maybe the universe isn't just a place we live in, but a process that never stops building itself. And if that's true, then what we've seen so far, particles, atoms, stars, life, and even thought, might just be the beginning. But before we can follow that thought too far, there's another layer we need to understand. Because emergence doesn't just build complexity in space, it builds it in time. And if there's one illusion that has shaped how we see every other layer, it's the one we're about to pull apart. Let's settle into this next layer, because if emergence showed us how reality builds itself step by step, this is where we pull at the thread that has been running through every single layer without us even noticing it. This is about time. Not the way you check it on a clock or feel it in the quiet stretch between morning and night, but what it really is underneath all the ways we've learned to measure it. And here's the part that might be hardest to take in. Time may not be what we think it is. It might not even be constant. It could be something far stranger, something we've been carrying like an unquestioned assumption, even though reality has been hinting all along that it isn't quite what it seems. On the surface, time feels simple. You wake up, the day moves forward, hours pass and they all stack neatly one after another, never doubling back or skipping ahead. It's so ingrained in how we experience the world that it's almost impossible to imagine it working any other way. But physics has been quietly dismantling that picture for over a century. Because when you dig down deep enough, time isn't steady. It doesn't tick for everyone in the same way. In fact, it doesn't even have a single universal flow. Einstein was the one who broke it open. His theory of relativity didn't just describe how space bends. It showed that time bends with it. If you move fast enough, time slows down for you. If you sit in a strong enough gravitational field, time stretches, running at a different pace than it does for someone farther away. This isn't speculation or theory anymore, it's measurable. Astronauts aboard the International Space Station experience time slightly differently from people on the ground. The difference is tiny, but it's real. Even the GPS satellites that orbit the Earth wouldn't work if we didn't correct for this effect. Time is not constant. It changes depending on where you are and how you move. And then there's the way the universe treats time at the deepest level of its laws. Look at the equations that describe physics, the ones that govern particles, fields, and forces. Most of them don't even require time to move in one direction. They work just as well forward as backward. Nothing in the fundamental machinery of reality says time has to flow from past to future. The arrow of time, the thing we take for granted every time we see a clock tick forward, is something that only seems to appear at the scale we live in. And the only reason we think of it as moving one way is because of entropy, the tendency for things to spread out, to settle into disorder. Think about that for a moment. Everything you've ever done, every moment you've ever experienced feels tied to this forward flow. And yet, deep down, the universe doesn't seem to care about that flow at all. It just happens to look that way because we exist in a world where entropy gives us direction. But it gets stranger. Because if time isn't constant and it doesn't even really have a built-in direction, then maybe it's not a fundamental part of reality at all. Some physicists have started to argue exactly that. They suggest that time is an emergent property, something that arises from deeper laws in the same way temperature arises from the motion of particles. Temperature isn't a thing on its own, it's the collective behaviour of countless tiny parts, and in the same way, time might be nothing but a kind of large-scale illusion, built out of something more basic. That's not an easy thought to sit with. It means that past, present and future might not be separate places lined up one after another. They might all coexist in a single structure, like pages in a book. We move through them in one direction because of how we experience the world, but in the larger sense, every moment might already be there. The universe doesn't flip pages for us. We're just sliding across them one after another, carried forward by the way our minds process change. And if that's true, then what does it mean for the way we live? What does it mean for memory, for the way we tell stories, for the way we think about the future? If time is just a construct, then all of the moments that make you who you are, the decisions, the accidents, the small quiet seconds that no one else noticed, they might still be sitting there, not gone, but simply not where you are right now. It's unsettling, but it's also oddly comforting. Because if time isn't a constant river, if it's not even a single thread, then maybe nothing is ever really lost. Maybe everything that has ever happened is still out there, written into the fabric of the universe in a way we just can't see. And yet, even with all this strangeness, there's another layer waiting underneath. Because if time is a construct, if it's not truly fundamental, then what is? What holds reality together when you take away the one thing we've been using to hold our lives in order since the beginning? If time can bend, stretch, and even dissolve into something that isn't truly fundamental, then we have to ask what sits deeper than that. What lies beneath time, beneath space, beneath matter, and even the strange haze of quantum rules? This is where we find something that doesn't look like a force or a particle at all, and yet everything in the universe seems to follow its lead. It's information, and more, it's beginning to look like it may be the true foundation of everything. When we think of information, we tend to imagine words, numbers, data stored on a screen or scribbled into a notebook. But in physics, information is different. It's not just facts or symbols, it's the arrangement of reality itself. Every particle, every field, every state the universe has ever been in is a kind of record, a pattern that can't simply vanish. And that's what makes information so strange. Because unlike energy or matter, it doesn't just change form, it persists. This idea became unavoidable when scientists started studying black holes. For a long time, black holes seemed like the ultimate erasers, swallowing anything that crossed their event horizons and hiding it forever. But that created a problem. If information about what fell in was truly gone, it would break the laws of physics. Reality would stop being predictable. The universe would lose its ability to keep track of itself. And then came a series of discoveries, ideas from Stephen Hawking, from Jacob Bekenstein, from others who stared at the edge of those impossible objects, and slowly the picture shifted. It turned out that information isn't destroyed when it falls into a black hole. It gets encoded, smeared out across the surface of the horizon itself, stored in a way we can't easily read but that never disappears. This was more than just a fix to a puzzle. It was a hint that information is not just another thing in the universe. It's the thing the universe refuses to lose. And once you start looking at reality through that lens, everything changes. Matter and energy become secondary. Space and time become secondary. At the bottom of it all, what's left is information. Bits and relationships. a cosmic network of yes or no states that form the scaffolding for everything else. Some physicists even argue that the universe itself may be a kind of quantum computer, not a machine sitting in a lab, but a natural engine in which every interaction, every particle collision, every fluctuation of a field is a calculation. The stars, the planets, the empty void between them, it's all the result of the universe processing information step by step like a vast unending program. And strangely, this isn't just speculation. We already see hints of it everywhere. Quantum mechanics, at its core, is about information. What can be known, what cannot be known, and how observation changes the state of a system. Thermodynamics, the science of heat and energy, turns out to be tied to information as well. Entropy, that steady drift toward disorder that gives time its arrow, is really a measure of missing information. Even space-time itself might be built from informational threads. Some researchers have proposed that the fabric of the universe, the very geometry of space, could emerge from networks of entangled bits of quantum information. If that's true, then reality is not made of things, it's made of relationships. And everything we see, particles, fields, even time itself, is just what happens when information organizes itself into patterns stable enough to feel real. And if that's the case, then we've been living in the middle of something far stranger than we realized. Because information doesn't vanish, it doesn't wear out, it only changes form. The universe remembers everything, from the fusion of the first stars to the movements of galaxies to every flicker of thought in your mind. But here's what's even more startling. If information is fundamental, then it doesn't just describe reality, it might be reality. That means the difference between the universe as it is and a perfect digital simulation of it might be smaller than we think. Not because we live in a computer, but because computation and physics may turn out to be two ways of talking about the same thing. And if that's true, then information isn't just the code of the cosmos, it's the only thing that never stops running. Stars burn out, galaxies drift apart, time stretches, but the information underneath it all never goes away. And yet, for all its permanence, this layer doesn't feel final. Because if information is the bedrock, we still have to ask what's built on top of it. How does something so abstract turn into the world we know? How does it give rise to matter, motion, and everything we can touch? If information is the foundation that quietly holds everything together, then the next step is where the questions stop being only scientific and start bleeding into something else. This is where physics meets philosophy, not in debate, but in a kind of uneasy partnership. Because once you go deep enough into the layers of reality, the line between what can be measured and what must be interpreted begins to blur, and suddenly the tools of science and the questions of philosophy are staring at the same thing from opposite sides. It starts with the limits. Physics, for all its precision, is built on observation and math. It tells us how the universe behaves with astonishing accuracy, but it doesn't always tell us why. We can write down the equations for gravity, for quantum mechanics, for the evolution of the cosmos itself, and they work. They match the world. But if you ask what those equations really mean, what they say about the nature of existence, you run into silence. This is where philosophy has always lived, in the spaces the equations leave behind. Questions like whether time is real or whether it's an emergent property, whether the universe is made of particles, fields, or pure information, whether consciousness is a side effect of matter, or whether matter is a side effect of consciousness. Physics doesn't settle these questions, because they aren't the kinds of things you can test with a single experiment. But they're not meaningless either, because the deeper science digs, the more it keeps finding itself standing on their doorstep. Take quantum mechanics. On one side, it's the most successful theory in all of science. It predicts the behavior of particles with such accuracy that we can build technologies that depend on it. But what it actually says about reality is a mess of competing interpretations. Does the wave function collapse when you look at it? Or does every possible outcome happen in branching universes? Is the randomness real, or is it hiding some deeper layer we haven't found yet? The math doesn't pick a favourite, it just works. And yet, we can't stop asking what it means, because what it means decides what kind of universe we think we live in. Or look at the nature of the laws of physics themselves. Why are they what they are? Why these equations and not others? Physics describes them, but it doesn't explain them. It doesn't tell us why the universe allows complexity, or why it has constants that seem finely balanced enough to let stars burn and life appear. Is it chance? Is it necessity? Is it something else entirely? Here, physics hands the question off to philosophy whether it wants to or not, because this is the point where how stops and why begins. And then there's the question of the observer. In a purely physical sense, you're a system of particles and fields. But in every meaningful sense, you're also the thing that experiences all of it. What happens when that perspective is no longer just a detail, but a fundamental part of the story? Physics can trace neural activity in the brain, map the pathways of thought, even simulate aspects of decision-making. But it cannot answer why any of it feels like something. And yet, without that feeling, without consciousness, reality is nothing but an empty stage with no one to witness it. This is why the deepest layers of reality always seem to loop back to philosophy, because the closer we get to the foundation, the more we're forced to confront the fact that science isn't just describing a world out there, it's also tangled up with the fact that we're in here, trying to see it. And that means the most fundamental questions about the universe are also the most personal ones. But maybe this isn't a conflict. Maybe it's the point. Maybe physics and philosophy are two ways of looking at the same thing, one with numbers, the other with questions, and they only seem separate because we're still standing too far back to see how they fit together. And if that's true, then what waits below this layer is even stranger. Because there's a place where physics begins to stretch out toward the horizon, to the very edge of what can be known. It's where we stop talking about what we've seen and start talking about what might exist beyond the part of the universe we'll ever be able to reach. If physics and philosophy meet in the questions we can't stop asking, this next layer pushes us to the very limits of what we can see, and then past that into the places we can only imagine. This is where the map of the universe ends, where the observable horizon fades into darkness, and what lies beyond it is something we can't measure but can't quite ignore either. This is the edge of the observable. When you look up at the night sky, every star you see, every galaxy captured by telescopes, sits inside a bubble, a sphere defined by how far light has been able to travel since the beginning of time. That distance is about 46 billion light-years in every direction. It sounds enormous, but it's only a piece of the whole. Beyond that, there is more universe. We know it. We just can't see it. Light from those regions hasn't had enough time to reach us. And here's the unsettling part. What we can see might be the tiniest fraction of what's actually out there. The universe doesn't have to stop at the horizon we can observe. It could stretch out forever, expanding endlessly into distances we'll never touch. Everything we've measured so far, billions of galaxies, each one filled with billions of stars, could be nothing but one small local patch of something far larger. But it gets stranger, because the edge of the observable universe isn't just about distance, it's about time. When we look at galaxies near the horizon, we're not seeing them as they are now. We're seeing them as they were billions of years ago, frozen in light that's been travelling toward us since the early universe. Beyond that horizon, there might be entire regions that have evolved in ways we could never predict. Maybe there are galaxies we'll never see, stars that burned out before their light could even reach us, or vast empty spaces where nothing ever formed at all. And then there's the expansion. The universe isn't static. Space itself is stretching, and the farther away something is, the faster it recedes from us. Eventually, anything beyond a certain distance moves away faster than light can bridge the gap. It's not breaking any laws. This isn't motion through space, but the expansion of space itself. And it means that, piece by piece, the cosmos is disappearing from view. Galaxies we can see today will one day slip over that horizon, their light stretched into invisibility until they're gone from our sky forever. So what does that leave us with? A visible universe surrounded by a vast, unreachable beyond. A boundary not of walls but of time and distance. A horizon we can never cross no matter how advanced we become. And if that sounds final, remember this. Just because we can't see it doesn't mean it isn't there. The edge of the observable universe isn't the edge of reality. It's only the edge of what we've been allowed to witness so far. But there's another possibility, one that makes this horizon even stranger. Inflation theory, one of the leading explanations for the early universe, suggests that in the first fraction of a second after the Big Bang, space expanded faster than light. And if that's true, then what we can see is just one bubble in an infinite froth of other bubbles, other regions of space, each with its own galaxies, its own stars, its own paths of evolution. Some of those regions might be almost identical to ours. Others could be unrecognizably different. And if the math is right, there may be infinitely many of them. That's not just distance anymore. That's a scale so large it erases the meaning of out there. We would live in one tiny patch of an unending cosmic quilt, stitched together by the same laws but far too vast for us to ever grasp all at once. And then comes the quietest, strangest thought of all. If there's an edge to what we can observe, and if there's more universe beyond it, then maybe our little horizon isn't just a boundary, it's a reminder. A reminder that the part of reality we see is never the whole story. But instead of feeling small in the face of it, there's another way to look at it. The horizon isn't a wall, it's a promise. It's the universe saying there will always be more than we can reach, more than we can measure, more than we can fold into neat equations. The horizon we can see and into the darkness that outweighs everything we've ever known. Because if the edge of the observable universe showed us how much we'll never reach, this layer shows us something even more unsettling. Most of what's here has been invisible all along. The stars, the galaxies, the entire sparkling structure of the cosmos is only a thin surface. Underneath it, around it, and running through it is something we can't see, can't touch, and can barely measure. This is the great unseen, dark matter and dark energy. Start with dark matter. For a long time, astronomers assumed that what we could see, the glowing stars, the swirling gas clouds, the bright arcs of galaxies, was most of what the universe contained. But when they looked closer, when they measured how galaxies spin, something didn't add up. The stars at the edges of those galaxies were moving far too fast. By all rights, they should have been flung out into the void. And yet they stayed, locked in place, as if held by a gravity stronger than what visible matter alone could provide. The only explanation was that something else was there, something invisible that didn't glow or shine, but that had mass, pulling with its quiet, unseen weight. We call it dark matter, not because it's made of shadows, but because it doesn't interact with light. It doesn't absorb it. It doesn't reflect it. It simply passes through, hidden, except for the way it tugs on the things around it. And there's a lot of it. In fact, it's not just a small correction, it's the majority. For every bit of matter we can see, there's about 5 times as much dark matter wrapped around it, sculpting galaxies into their shapes, gathering them into clusters, holding the cosmic web together. Without it, the universe as we know it wouldn't exist. Stars wouldn't have formed, galaxies wouldn't have stayed bound, the night sky would be empty. And yet, for all that, we don't know what dark matter actually is. We've built detectors buried deep underground, shielded from cosmic rays, waiting for the faintest whisper of a collision with one of these invisible particles. So far, nothing. It's there, We can see its gravitational footprint everywhere, but it stays just out of reach, like a ghost woven into the structure of the universe. But dark matter is only half of the great unseen. Because when we look not at how galaxies hold together, but at how the universe itself moves, another mystery appears. For a long time, we thought the expansion of the universe should be slowing down. Gravity pulls everything together after all, so it seemed obvious that over time the growth of the cosmos would decelerate. But then we measured it, and what we found was the opposite. The expansion isn't slowing down, it's speeding up. Space itself is stretching faster and faster, pushing galaxies apart, driving them over the horizon where we'll never see them again. And the only way to explain it is to assume that there's something else at work. A form of energy built into the fabric of space itself, a kind of pressure that counteracts gravity and drives everything outward. We call it dark energy, and it doesn't just exist, it dominates. Nearly 70% of the universe is dark energy. 25% is dark matter. That means that everything we've ever studied, every planet, every star, every galaxy, is less than 5% of the whole. The rest is hidden, not because it's far away, but because it doesn't reveal itself in any way our senses were built to see. And that's what makes this layer so difficult to sit with. It's not just that there's more universe out there than we can reach. It's that most of the universe is already here, wrapped around us, pressing in on every side, and we're living in the thin, visible skin of it, like it's the whole thing. And yet, even though dark matter and dark energy sound alien, they're not separate from us. They shape the world we live in every second. The invisible halo of dark matter around our galaxy is the reason the stars haven't flown apart. The push of dark energy is the reason the night sky is thinning out as galaxies rush away faster than light will ever bring them back. We are surrounded, carried, and quietly sculpted by things we can't even see. But here's the strangest part of all. These two great unseen forces don't just dominate reality. They may be the key to the layers we haven't reached yet. Because if we could understand them, if we could find out what dark matter is made of or why dark energy drives the expansion of space, it might force us to rewrite everything we thought we knew about the foundation of the universe. And maybe that's why this layer doesn't feel final either. It's not an answer. It's a reminder that the visible world, the part we move through and trust, is only the beginning. But if this is what reality looks like when most of it is hidden, then what would reality look like without us in it at all? If we could strip away the human perspective, the colours, the sounds, the sense of scale, what would be left? If dark matter and dark energy showed us that most of the universe is invisible to us, this next layer asks an even colder question. What happens when you remove us entirely? What does reality look like without eyes to see it, without minds to measure it, without anyone to give it meaning? This is the view of a universe unaware of itself. Imagine turning off every observer. No humans, no animals, no life of any kind. The stars would keep burning, galaxies would keep spinning, the fabric of space-time would still stretch outward, driven by dark energy, dragging countless clusters of galaxies farther and farther apart. Nothing would stop, nothing would pause, but there would be no one to witness any of it. Without us, the universe would not become smaller or less real. It would simply be indifferent. And maybe it already is, because the rules that govern reality, gravity, quantum mechanics, the dance of particles and fields, don't require anyone to look at them. They were here before we appeared. They will be here long after we're gone. But this is where things get strange, because even though the universe doesn't need us, we still change the way it unfolds, at least at the quantum level. In the smallest scales we've explored, observation doesn't just record reality, it helps define it. An electron exists in a haze of possibilities until it's measured. A particle is nowhere in particular until we ask the question that pins it down. If there's no one left to ask, does reality still choose? Or does it drift forever in a blur of maybes with no one there to make it settle? Some physicists argue that it doesn't matter. The universe doesn't wait for an observer. It interacts with itself. Particles collide, forces act, measurements happen whether or not anyone is around to write them down. But others point out that consciousness, however small its role might be, is the only reason there's such a thing as experienced reality in the first place. Without it, there would still be a universe, but would there be anything that could be called now? And maybe this is the part that's hardest to think about. Even if we vanished, the universe would keep going, but not in a way we could ever really imagine, because imagining requires someone to be there. We are so used to folding ourselves into the picture that it's almost impossible to remove the lens of awareness entirely. And yet there's something humbling about trying, because it forces you to see the universe not as a stage built for us, but as a thing in its own right, a place that doesn't ask for permission, a place that doesn't care if it's seen. Think about the first stars. They burned for billions of years before there was anything around to name them. Think about the galaxies at the edge of the observable horizon, their light still racing toward us across distances so great we'll never catch up. They shine in absolute silence, not for us, not for anyone, just because that's what they do. And maybe that's what the universe really is when you strip us out of it. A vast, unending process with no audience. Stars are born, stars die, black holes form, space-time bends, particles shift in ways no one will ever measure, and it all just happens, whether or not anyone is there to notice. But here's the strange twist. Even if the universe is indifferent, even if it doesn't need us, it still produced us. Every particle in your body was forged in a star that never knew you'd exist. Every breath you take is built from atoms that spent billions of years wandering through a universe that was perfectly fine without you, until somehow, for reasons no one has fully explained, those atoms came together and learned to wonder what they were made of. And that's the paradox we're left with. A universe that doesn't need consciousness somehow gave rise to it anyway. And once that happened, the universe was no longer entirely unaware. For the first time, at least in this small corner of it, there was something looking back. But what if there's more to it than that? What if consciousness isn't just an accident, but part of the same structure as everything else we've been uncovering? What if even in a universe without us, there are patterns so deep they don't just exist? They give rise to awareness again and again, no matter how many times it fades out. If we've come this far, through matter and fields, through time and information, through a universe that doesn't even need us, then there's one more layer waiting, and it's not like the others. This one doesn't add anything new to the stack. It doesn't reveal a deeper particle or a hidden force. Instead, it changes the way we see everything we've already passed through. It's the place where the chaos of reality starts to reveal its order. This is the layer of patterns in the noise. At first glance, the universe looks random. Stars scatter across the sky in no obvious design. Galaxies spin in every direction. Particles jitter and fluctuate in ways that feel meaningless. Even our own lives are filled with coincidences, accidents, events that seem to happen without reason. But the closer you look, the harder it is to ignore the fact that none of this is truly random. There are structures hidden in the apparent mess. The deeper you look, the more the noise starts to form a shape. Take the cosmic web. On the larger scales, galaxies aren't scattered evenly through space. They form vast filaments, sprawling chains of matter that stretch across hundreds of millions of light years, woven together like threads in a cosmic fabric. Between them are enormous voids, empty spaces where almost nothing exists. It looks chaotic if you only focus on one small patch of it, but when you pull back far enough, you see the design, and the same thing happens on smaller scales. Look at particles in quantum mechanics. Yes, they seem unpredictable, jumping from one state to another, their locations uncertain, their behavior governed by probability. But when you gather enough of them together, they obey rules so strict you could set your watch by them. The apparent randomness washes out, and the pattern emerges. And it's not just physics. Even life works this way. Evolution is often described as blind, a process with no plan or direction. But when you step back, you see it's not just blind, it's relentless. It takes simple rules and applies them over and over until something vast and intricate emerges. From single-celled organisms to entire ecosystems, from neurons firing in the dark to thoughts that can map the stars, the same principle repeats, patterns rising out of what first looked like noise. Maybe this is what the universe really is, not a clean hierarchy of layers stacked neatly on top of each other, but a single structure made of patterns repeating at every scale. Particles become atoms, atoms become molecules, molecules become life, life becomes thought. And none of it is separate. Each layer folds back into the others, not as isolated floors in a building, but as echoes of the same underlying rhythm. And here's the strange thing. We keep finding that rhythm in places we didn't expect. The same equations that describe the growth of galaxies can also describe the branching of trees. The mathematics that governs the orbits of planets can also describe the flow of a river. The universe reuses its own rules in different disguises, over and over, like a song that keeps returning in a different key. If that's true, then maybe this final layer isn't really final at all. Maybe it's what's been here the whole time, hidden under every other layer we've passed through, from the quantum foam to the cosmic web. The patterns were always there. We just needed to step back far enough to see them, and this changes the way you look at everything. It means the noise isn't meaningless, the chaos isn't empty, it's just complexity we haven't unraveled yet. What looks random at one scale might be the start of a pattern too large or too small for us to recognize. But here's the most humbling part. If reality is built this way, if it's patterns all the way down, then there may never be a single point where it ends. No final equation. No last answer. Just an endless unfolding, each layer giving way to another, each pattern revealing a larger one above it. And maybe that's not a flaw. Maybe that's why the universe can exist at all. It doesn't need a bottom. It doesn't need a final piece. It only needs rules simple enough to repeat forever, until from that repetition comes everything. The stars, the galaxies, and the quiet awareness that sits here wondering how far down it all goes. And if that's true, then what we've been doing all along, moving down through each layer, was never about reaching the end. It was about learning how to see the structure for what it is, and once you see it, you can't unsee it. But we're not done yet, because there's one last step we need to take. Not downward this time, not outward, but back to where we started. Because after everything we've uncovered, after all these hidden layers, we need to return to the surface and look at it again with new eyes. Let's bring this journey full circle, not to end it, but to return to where we began, only now with a different way of seeing. Because after everything, the atoms and quarks, the fields and space-time, the strange pull of gravity, the unseen oceans of dark matter and dark energy, the branching paths of parallel realities, the possibility of information as the true foundation of existence. After all of it, we're back here, sitting in the quiet, between the noise of the day and the steady hum of the universe, somewhere in the middle of it all. Look around you, or just close your eyes and imagine it. The chair you're in, the air you breathe, the room holding you. It feels solid, familiar, ordinary. But you know what's under it now? You know that every inch of that solidity is built from emptiness and forces, from particles that only exist as probabilities until they're pinned down, from fields stretching invisibly through space, binding it all together. The ordinary world hasn't changed. You have. And maybe that's what this whole descent has been about, because reality hasn't become less real the deeper we've gone. It's become larger. It's become stranger. And in that strangeness, there's a kind of quiet comfort. Because the more you see how many layers there are, the easier it becomes to stop looking for a single, final answer. Instead, you start to rest in it. And if you sit with that for a moment, you notice how it shifts the way you think about even the simplest things. Time doesn't just pass, it stretches and bends. Space isn't just emptiness, it's a fabric, curved by every mass it holds. The stars you see at night aren't just points of light, they're ancient messengers, their glow carrying the story of what they were long before you existed. And the best part is, none of it is separate. You're made of the same particles that hum in the heart of a star. The same fields that ripple through empty space run through you. You are, quite literally, a piece of the universe looking back at itself. But even knowing all of that, the surface world doesn't go away. You can still hold a cup in your hand. You can still feel the ground beneath your feet. You can still breathe and laugh and live inside the thin, visible skin of reality, even while you know that underneath it all, there are layers without end. And maybe that's where the real peace is. Not in answers, but in the space between them. Not in reaching the bottom, but in realizing that the search itself is what keeps us moving through it. So here we are, resting between realities. Not at the end, because there isn't one, but in a place where we can finally stop climbing downward for a moment and let it all settle in. And if you're listening to this right now, if you've come with me through every layer, then maybe you can feel it too. The quiet hum of a universe that is both infinitely deep and close enough to touch. And that hum isn't asking you to solve it. It isn't asking you to understand every piece. It's just there, steady and patient, like gravity, like the slow expansion of space, like the patterns that keep emerging no matter how deep we go. So let's stay here for a little while longer. Not because there's nothing left to see, but because for now, it's enough. Enough to know that every question only opens another door. Enough to know that we live inside something bigger than we can hold in our minds. Enough to know that there's no rush to get to the bottom because there is no bottom, only the next layer and the one after that waiting quietly in the dark. And if you found this comforting, if there's something in this slow walk through the hidden scaffolding of existence that's made the world feel a little wider, a little quieter, maybe you'll stay with me for the next one, because there's always another question. There's always another layer. But for now, let's just rest here. Between the ones we've seen and the ones we haven't reached yet, the universe isn't going anywhere, and neither are we. Alright, let's close this out. Not with an ending, but with a pause. Because if there's anything this whole descent through the layers of reality has shown, it's that there is no final stop. There's always one more question. One more hidden piece, one more quiet turn in the story that reminds us how much is still out there, waiting. So thank you for coming with me through all of it, from the atoms that make you to the stars that burn billions of light years away, from the bending of space-time to the invisible weight of dark matter and the quiet hum of information underneath it all. And if you've stayed here, listening through every step, then maybe you already know the truth. The universe isn't something you solve, it's something you live in. And maybe in a way that's better, because it means we don't have to rush. We don't have to finish the puzzle. We only have to keep looking, keep wondering, and keep resting for a moment in the space between what we know and what we don't. If you found some comfort in that, if this little journey has made the world feel just a bit quieter, or stranger, or more alive, then stay with me. There are more layers, there always will be. So take a breath, let the questions settle for now, and remember, the universe is still humming, whether or not you're listening, and if you are, well, you're already part of it.